Today's topic is special segments and circles, and you can use the date of May 20th. This is officially our last note packet for this year. These are the 4 note pages that you'll need for today's lesson. They should be the last materials in your round 2 packet. All right, we've previously talked about chords in a circle. Chords are line segments that start and end on the circle itself. They can be different sizes and they don't necessarily pass through the center of the circle. But it is possible for the chords to intersect inside the circle. So this diagram shows 2 chords intersecting. So our first theorem says that if 2 chords intersect in a circle, that the product of the parts on the first segment, so AE times EB, equals the product of the segments on the second chord, CE times ED. So none of the parts are necessarily equal. The chords are not necessarily equal. It's just the product. The result of multiplication, those will be equal. Let's try a simple example. So we have numerical values for 3 of our pieces, and the 4th one is X. We have to find the value of X. So we're going to start by multiplying the pieces on QP, 9 times X, and that is equal to the product of the pieces on ST, 3 times 6. So if we follow through with our math, we know that the missing piece, X, is 2, and we can check that theory. 9 times 2 is 18, 3 times 6 is 18. The products are equal, but the pieces and the parts are not. In our past lessons, we've talked about secants. We know that a secant will pass through and touch the circle in 2 distinct locations. The secant can also be a segment where part of it is outside the circle. The external secant segment is outside the circle, and this will be important in our future calculations in this lesson. So theorem number 2 says if you have 2 secants in a circle, to find the missing pieces or any part on the secant, we're going to take the external portion and multiply it by the whole, and then it will be equal to the external portion on the other secant times the whole secant itself. What I've done is the external pieces are highlighted in red, so it's EA times the whole secant EB, and that product is equal to EC, the external portion on the other secant, times the whole segment itself, ED. Again, the secants are not necessarily equal. The interior and exterior pieces are not equal. It's just the product is equal. Let's try this example. They're asking us to find the value of X. So it'll be the external portion, 9, times the whole secant, which is 9 plus 11. And it's equal to the external portion, 10, times the whole secant, 10 plus X. We're going to clean things up a little bit and distribute. So 9 times 20 will be 180, and when I distribute, I have 100 plus 10x. We're going to combine like terms, and we'll see that x is 8. So again, the pieces and parts are not equal. The secants themselves are not equal. It's just the product of the external piece times the whole. Those were equal. In our third theorem, we're using 1 secant and 1 tangent. Remember, tangents only hit a circle in one spot. So if this is the setup that we see, we're going to take the external tangent piece and we're going to square it. And that's equal to the external secant piece times the whole secant. So let's try an example. We're going to find x in this case. What I did put on here is that x represents a radius, but in fact we need 2 of those sections, so I added another x here. So it'll be the tangent piece squared, and that equals the external, 12, times the whole secant, 12 plus x plus x. We're going to square and distribute, When we combine like terms, we see that the value of x is 18. We've been through all through theorems. The first 8 examples are going to relate to theorem number 1. So remember, we're multiplying the pieces of the segments. So 2 times x equals 3 times 6. And we see that x is 9. And we see also that 2 times 9 and 3 times 6 are both 18. In number 2, we have a diameter hitting a chord in a perpendicular manner. We learned in our last lesson that when that happens, the chord is bisected. So we'll have x times x. It equals 2, which is the small piece of this segment. And then we need to multiply by this entire segment. The radius is 10, but the piece from the center to the chord is 8. So you want to keep some of those things in mind when you're setting up your equation. So when I solve my equation, my missing piece of x equals 6. In number 3, when we set this equation up, it's 6 times x equals 8 times 8. In this case, x is not a perfect number. We'll round it off to the nearest tenths as directed in the instructions. With number 4, x times the quantity of x plus 7. Don't forget to put that in parentheses or we'll have a distributing mistake, and that equals 3 times 6. When I distribute, I will have a quadratic equation, and I did move the 18 over so that all the terms were on the same side. We're going to factor our quadratic. So we need two numbers that multiply to negative 18 and also add up to 7. The factors are x plus 9 and x minus 2. And when I set these factors equal to 0, one root is at negative 9. We cannot have a segment length that's negative. It doesn't make any sense. So we'll accept the second root, saying that x equals 2. In number 5, you can see that these segments do intersect in the center of the circle. So instead of making this more difficult, we know that the radii are equal. So x plus 2 does equal 5, and therefore x equals 3. In number 6, we had a problem similar to this already. Both of these pieces on the chord are x. So x times x, and then it's 2 and times the entire piece of this segment. So the radius is 7, but this tiny little piece in here is 5. So the square root of 24 is not perfect, and we will round it off to 4.9. With number 7, we're multiplying 2x times 3x, and that equals 6 times 5. When I distribute and combine, I'm going to divide now by 6, and 5 is not a perfect square, so the value of x is approximately 2.2. We'll do the same in our last example. 3x times x equals 6 times 8. We're going to divide both sides by 3, and this is a perfect square. So even though x has 2 roots, we're going to disregard the negative 4 as a reject and accept positive 4. Now, the next set of examples are going to use theorem 2 and 3. We're going to find the value of x, and we'll round to the nearest tenth when necessary. So in number 1, I have a tangent piece. So it'll be 3.3 squared. And then it equals the external secant piece times the whole secant. We're going to square and distribute. We'll combine our like terms and divide by 2.2. So x is rounded to 2.8. In example number 2, we're using two secants. So it's going to be external times the whole. 16 plus 26 equals the external times the whole, 18 plus x. We'll combine like terms, distribute. And when I divide by 18, the value of x is approximately 19.3. In number 3, we can see the tick marks indicating that those pieces are both 8. Again, we're dealing with two secants, so it's external times the whole, and that whole secant is 16, and then it's external times the whole. We'll distribute and combine, and x is approximately 7.7. In number 4, we're back to using a tangent piece, so we're going to square 13, and then its external times the whole. Let me square and distribute, combine like terms, rounded x is 2.8. In number 5, we're using 2 secant pieces, so it'll be the same for the top secant and the lower secant. It'll be external times the whole and external times the whole. I'm going to go ahead and add 6 plus 3. So when I distribute the 6 times 9, it'll be 54. I'm going to subtract 36 from both sides first. And now I'm going to subtract 6x from both sides. And that will tell me that x is 1. Hopefully you're getting the hang of these. In number 6, it's 2 secants, external times the whole equals external times the whole. When I distribute again, I see a quadratic term pop up. I'm going to go ahead and subtract 80 so all my terms are on the same side. And I'm going to factor. I need 2 numbers that multiply to negative 80 and then add up to 11. Our factors are x plus 16 and x minus 5. My first root is at negative 16. We're going to reject that option as it doesn't make sense for the problem. The second root is at x equals 5, and that one does make sense, and we'll accept that answer. In number 7, it's a tangent and a secant. So we'll square 35, and then it's external times the whole. And combining like terms and solving. X is 37.3. In number 8, the diagram looks a little strange. This little piece that is represented by x is a tangent. This other section is 5. From the center to the circle, this is also a radius. This piece is also 15. So be careful. I want to square my tangent piece, and then it's the external 5 times the whole secant. So combining like terms and multiplying, the square root of 175 is rounded to 3.2. In our last example, this piece outside is x. We do have a tangent. Keep in mind from the center of the circle to the edge, we have 6 more units right there. So tangent squared equals external times the whole. In this problem, I'm going to obtain a quadratic term. So I'm going to subtract 64 from both sides. When I factor, my 2 binomials are x plus 16 and x minus 4. So the root at negative 16 will be rejected, and we will accept an answer of 4. Tonight's homework are these 2 pages. This is number 130. Please make sure you show all work, and don't forget I'm spot checking and taking a quiz grade at the end of the week. If you have any questions on the last set of notes, please make sure you contact me. Otherwise, have a great day.